Hey everyone, and welcome. Today, we're going to demystify a machine learning technique that sounds super complicated but is actually one of the most powerful tools in your entire toolkit. We're talking about Principal Component Analysis, or PCA. We're going to break it down and show you how it turns a total mess of data into something clear, simple, and incredibly useful.
So let me ask you something. You know that feeling when you get a brand new data set and you're all excited to get started, but then you see it has dozens, maybe even hundreds of different features? It feels like your model is just drowning in information before you've even begun. Where do you even start?
Well, that exact problem has a name, and it sounds as spooky as it feels: the curse of dimensionality. And trust me, it's the real villain of this story. See, having too many features or dimensions can slow your model training down to an absolute crawl. It can make it way too easy to overfit, and visualizing it, forget it. Our brains just aren't wired to plot data in 100 different dimensions.
So, how do we fight back against this curse? The strategy is called dimensionality reduction. And the mission is pretty straightforward. We need to shrink the number of features in our dataset. But, and this is the important part, we have to do it without losing the essential story that the data is trying to tell us.
Okay, I love this analogy. Think of your big, messy, high-dimensional data set as a 3D object, like a spinning chair. You can't possibly see all of its sides at the exact same time. Well, dimensionality reduction is like shining a light on that chair to cast a simple 2D shadow on the wall. Sure, you've lost a dimension, but that shadow, it still captures the most important stuff: the chair's basic shape and how it's moving.
And the most famous, the most powerful hero we have for this mission, the algorithm that knows exactly where to shine the light to cast the most informative shadow, is Principal Component Analysis, PCA. That's our focus today.
All right, let's dive in. How does PCA actually pull this off? How does it look at all that data and figure out what the principal or most important part of the story is? How does it know what to keep and what it can afford to let go of?
So here's the really clever part. PCA doesn't just go in and delete columns it thinks are boring. Nope, it's way smarter. It creates brand new, super-powered features called principal components. The first one, PC1, is this new direction that's custom-built to capture the absolute most variation, the most information possible in your data. Then PC2 comes along and captures the next biggest chunk of info, but, and this is key, in a direction that is completely independent of PC1. It literally ranks them by importance so you can keep the signal and just toss the noise.
Now, there is a lot of math going on under the hood here, but you really don't need to be a linear algebra expert to use this. At a high level, here's what happens. First, PCA puts all your features on the same scale so nobody gets an unfair advantage. Then, it figures out how all those features relate to each other. Next comes a bit of what we'll call linear algebra magic to find those new, powerful directions. And finally, it takes your original data points and just projects them onto these new components. Okay, theory is great, but let's make this real. We're going to see PCA in action with a fantastic example, the UN World Happiness Report. This dataset is basically a perfect candidate for what we're trying to do.
So here's the puzzle. For every country, you've got all these different features: GDP, social support, life expectancy, the list goes on. This is a 6-dimensional dataset. So how in the world are we supposed to look at all of that at once to figure out what really makes a country happy? The simple answer is you can't. And this is where PCA works its magic. It's incredible. After we run the algorithm, it turns out that the very first principal component, our PC1, explains a whopping 85% of all the differences in the data. The second one, PC2, explains another 10%. Think about that. Together, just 2 new features have captured 95% of the entire story from the original 6. We've taken a 6-dimensional problem and boiled it down to 2 dimensions, losing almost nothing important in the process. Now, a fair criticism of PCA is that these new components can feel a little abstract. What is PC1 really? But we can look at what original features contribute most to it and give it a name. In this case, PC1 seems to represent a country's economic and social muscle, so let's call it power. And PC2 seems to capture the relationship between social and individual factors, so we'll call that balance. For your models, this is absolute gold. You've just created 2 of the best super features you could ever hope for.
So when we actually plot the countries on our 2 new axes, power and balance, this amazing pattern just leaps off the page. The happiest countries, like you see in Scandinavia, They score high on both. They have lots of power and lots of balance. But now look at a place like Singapore. It's way up there on the power scale, mostly because of its high GDP, but it's much lower on the balance axis. And this reveals a deep insight that was totally hidden before. True national happiness isn't just about raw power, it's about having balance too.
So that's pretty cool, right? But let's bring it all the way back home. For you, as someone training machine learning models, what are the big practical payoffs here? Why should you add this to your workflow?
Well, it directly solves all those problems we talked about at the beginning. Your models will train so much faster because there's just less math to do. You can finally create these incredible 2D plots to spot hidden clusters and patterns. PCA also acts like a natural noise filter, automatically keeping the important signal and getting rid of the fluff. And maybe most importantly, by simplifying everything, it helps your model generalize better and is a fantastic weapon against overfitting.
But it's not a complete magic wand. We have to be honest here. There is one very important trade-off that you need to be aware of when you use PCA, and that's all about interpretability.
This slide lays it out perfectly. Your original features are great because they have clear, real-world meanings. GDP per capita, you know exactly what that is. But your new principal components, they're mathematical combinations of all the original features. So while PC1 is super powerful, you can't really point to it and say, oh yeah, that's just this one thing. So you gain a ton of simplicity and power, but you do lose a little bit of that direct, easy-to-explain meaning.
And here is one last fact that I just find amazing. PCA isn't some fancy new algorithm that came out of Silicon Valley last year. It was first invented by a guy named Carl Pearson all the way back in 1901. It is a foundational idea, over a century old, that has somehow become more essential in our modern world of big data and AI.
So that's our deep dive on PCA. It is an elegant, powerful, and truly time-tested technique for taming complexity. It lets you visualize the unvisualizable and find that core story that's hiding in all the noise. And that leaves us with just one final question to think about. What hidden patterns could PCA uncover in your data?